All right, let's talk about a really fascinating, kind of counterintuitive idea that's right at the heart of AI and machine learning. It's this weird problem that pops up when a model looks like it's doing its job perfectly, but in reality, it's heading straight for a total disaster.
So let's just jump right into the paradox. Imagine you've got an AI model, and it scores a perfect 100% on all the data it was trained on. I mean, that sounds amazing, right? That's the goal. But what if I told you that this perfection is actually a huge red flag? That it's often a sign of a model that's deeply flawed and honestly completely useless in the real world. How on earth is that possible?
Well, that's exactly what we're going to unpack. First, we'll talk about what I like to call the Goldilocks problem, this whole search for a model that's just right. Then, we'll look at the two extremes, overfitting, where a model gets way too complex, and underfitting, where it's just too simple. And finally, we'll get into the real-world dangers and the pretty clever ways engineers actually solve this.
So, let's get into it. You have to think of building a good machine learning model as a kind of balancing act. You're not looking for something that's too hot or too cold, but that thing that's perfectly in the middle, that sweet spot. And here is the absolute key to all of this. The goal isn't just to build a model that can perfectly trace over the data points it's already seen. No, the real goal is to learn the general pattern, that underlying trend, so it can make smart predictions about brand new data it has never seen before. You know, it's the classic difference between just memorizing something and actually understanding it.
To really nail this down, let's use an analogy we can all relate to. Studying for a test. You've got the overfitting student. This is the kid who crams and literally memorizes the answer to every single question on the practice exam, typos and all. Then you have the underfitting student, who just kind of skims the chapter titles and calls it a day. But the ideal student? They learn the actual concepts. That way, they can handle any question the real test throws at them. Keep these three students in your head.
Okay, let's start with that first student, the one who looks perfect on paper but really isn't. This is the world of overfitting. It's when a model gets obsessed with the details, when it learns way too much.
So the textbook definition is basically that overfitting is when a model's analysis gets way too close to its training data. Instead of learning a general rule, it starts memorizing all the little quirks and random noise in the specific data it was shown. At that point, it's not really learning anymore, it's just copying.
This slide shows the problem perfectly. See that wiggly green line? It hits every single training dot, which looks great at first glance. But the moment new data points appear, look what happens. It misses them completely. Now look at the simpler black line. It doesn't hit every point, but it successfully generalizes the pattern, and it does a much better job predicting where new data will actually land.
And here's an even more wild example. The red line manages to twist and turn and hit every single training data point. It gets a perfect score. But would you ever trust it to make a prediction about the future? No way. The simpler green line, even though it's not perfect, is a far more believable and useful model of what's really going on. Okay, so that's the danger of being too complex. Let's swing the pendulum all the way to the other side and see what happens when a model is just too simple. This is underfitting, when a model doesn't even learn enough to be useful.
This is our student who only read the chapter titles, remember? An underfit model is one that's so simplistic it just can't capture the real structure of the data at all, and misses important patterns and trends that are sitting right there, plain as day.
This side-by-side comparison makes it crystal clear. On the left, you can see the data points obviously form a curve, but our model is just a lazy straight line. It's missing the entire story. That is underfitting. But the image on the right shows a much better model, one that's complex enough to capture that curve without going totally crazy like our overfit examples. It's just right.
So let's put them head to head.
Overfitting is too complex, and it memorizes noise. In technical terms, that's high variance. Underfitting is too simple, and it misses the trend. That's called high bias. The overfit model looks fantastic on its training data, while the underfit model is just bad on everything. But here is the absolute kicker. Look at that bottom row. Even though they are complete opposites, they share the exact same fatal flaw. They both fail when it matters most, on new, unseen data.
So you're probably wondering, how did developers even know this is happening? Well, this graph right here is the smoking gun. The blue line shows the error on the training data, and as you can see, it keeps going down and down. The red line, though, shows the error on new data. At first, they both fall together, which is great. But then you hit a crucial point. See it? The training error keeps falling, but the error on new data starts to rise again. That's the warning sign. That is the exact moment the model has stopped learning and has started just memorizing.
Now, this isn't just some abstract, theoretical problem. Overfitting has serious, real-world consequences. But the good news is, there are also some powerful tools to fight back.
I absolutely love this quote from the source material because it just gets right to the heart of it. If a model generates something amazing just by randomly fitting to noise, does that mean it's intelligent? Or was it just lucky? Overfitting is the danger of mistaking dumb luck for actual skill.
And the dangers are no joke. At best, you just get faulty predictions that make your model useless, but it gets so much worse. An overfit model can actually memorize and then leak sensitive personal information that was in its training data. It can also lead to huge legal headaches, like the lawsuits we've seen against AI image generators for memorizing and then spitting out copyrighted material.
So, how do we find that Goldilocks zone? Well, developers have a whole toolkit. First, there's regularization, which essentially penalizes a model for getting too complex, pushing it to find simpler answers. Then there's cross-validation, which is kind of like giving the model a series of pop quizzes on data it's never seen, just to make sure it's really learning. Other techniques like pruning simplify the model by just removing unnecessary parts. Think of it like trimming dead branches off a tree. And finally, there's dropout, which forces the model to be more robust by randomly hiding parts of the data during training, so it can't rely on any one little piece of information.
So, the single most important thing to remember is this. In the world of AI, a perfect score on a practice test means absolutely nothing. The true measure of a model's success is its ability to take what it has learned and apply it robustly and reliably to the messy, unpredictable real world. Generalization, not memorization. That is the name of the game.
And that leaves us with a final thought to chew on. As these AI models get more and more powerful, and as they achieve results that look perfect on paper, will we become more tempted to just trust them without question? Could this fundamental flaw of overfitting actually become our biggest blind spot in the age of AI? Something to think about. Thanks for watching.